All right, sometimes when we're factoring, we have these situations that we call special cases. Specifically, we've got perfect square trinomials, and we've got difference of square binomials. All right, so there are kind of some shortcuts. We can still factor it the same way. We're still guessing and checking, but because of how it looks and what the numbers are, right, what makes them special is that they have to fit a very specific criteria. So it just narrows down our options. And if we remember that, it'll just make the process a little bit faster because we can decide which ones make sense and which ones don't make sense a little more quickly. All right, so that first one, if I'm looking at all of these first couple ones, we're not going to do them all, but if I'm looking at them, they all have the same thing in common. They're the form ax squared plus c. None of them have a bx term. So for all of them, bx must be 0. So if I'm thinking about letter A, x squared minus 36 is the same as thinking about x squared plus 0x minus 36. Well, I'm trying to factor this. The only way to multiply to be x squared is x times x. And I want something to multiply to be negative 36 and add to be 0. The only way for something to add to be 0, add or subtract to be 0, if it's a number minus itself. So when I'm thinking about 36, a lot of things multiply to be 36, but I only care about the one that's a number times itself, 6 times 6. Because if I had a positive 6 and a negative 6, 6 times x is 6x, x times negative 6 is negative 6. That's where my 0x comes in. That's why my b term disappears, because I had something minus itself. So I needed a positive and a negative of the same number. So really I'm thinking about perfect squares. So if I look at x squared minus 144, it's the same thing. I need something that multiplies to be negative 144 and adds to be 0. Well, that only works if it's a perfect square. I know that the square root of 144 is 12, so this must be a plus 12 and a minus 12. All right, letter C. This is a little bit different because I do have an a value other than 1, but it's got to fit that same pattern of something times itself. So even though I could think of 1 times 4 or 2 times 2, I know it's got to be 2 times 2. Right? Because we're thinking about in terms of perfect squares, and the square root of 4 is 2. What's the square root of 49? That would be 7. So one of these must be a positive 7. One of these must be a negative 7. Let's check our answer just to see. 2 times 2x is 2x, is 4x squared. There we go. 2x times negative 7 is negative 14x. 7 times 2x is positive 14x. 7 times negative 7 is negative 49. 14x and 14x, right? Minus 14x plus 14x, that's 0. It cancels out, and we get 4x squared minus 49. That matches our original quadratic, so we must have done this correctly. That's what we're saying. That's why that middle term is gone, because you had something times itself and it canceled out. All right, this next one, they're trying to trip us up here by throwing in that extra variable, but we're smarter than that. We know what something times itself. The square root of 16 is 4x. The square root of 100 is 10, so it must be 10y. Well, look at that. Look how easy that is when we recognize that pattern. All right, last two really quick here. 9x squared minus 1. Well, again, 9x squared, I know that must be 3 times 3. 1 is a perfect square, right? 1 times 1 is 1. So I must have a negative 1 and a positive 1. 3x minus 1 times 3x plus 1. Letter F, 25x squared minus 64. I know the square root of 25 is 5. I know the square root of 64 is 8. There we go. I could multiply it out to check, and I know that middle term would be 0. And again, remember, the order doesn't matter. If I had written 5x minus 8 and 5x plus 8, that's the same thing. That would be perfect. This is our difference of perfect squares, because we're subtracting things that are perfect squares, please note that all of these are subtracting. That's where the difference, right? The difference is subtracting. So it has to be subtracting in order to work. If it was an addition problem, that middle term wouldn't cancel out like it needs to. So it is important that it's a subtracting in your binomial for this to work out. All right. We're going to skip those two. We're going to go down to our perfect square trinomials. All right, so perfect square. What do we know about perfect squares? It's a number times itself. Okay, let's keep that in mind. X squared plus 18x plus 81. 81 is a perfect square. So there are a lot of things that multiply to be 81. If I can remember them all. Okay. I want the one that's going to add to be 18. 9 and 9 is 18. There's my perfect square. So this pattern, right, is saying it's a number multiplied by itself that gives you your C value, and added to itself gives you your B value. That's what makes it a perfect square trinomial. So this one might be, you have to think about it a little bit more, right? Because you have to be thinking about adding to be that middle number and multiplying to be your C value. But if you notice it, it's very nice. Let's do letter B. X squared minus 12x plus 36. 36 is a perfect square, everybody. So again, lots of things multiply to be 36. So if I was going to do just, my typical guess and check method, that would be perfect. I would still end up where I needed to be. I wanted to add to be negative 12. I know 6 and 6. Or negative 6 and negative 6 would be negative 12. So x minus 6 times x minus 6, that multiplies to be 36 and adds to be negative 12. And I can write this as x minus 6 squared, because squared, or to the second power, is how we write something times itself. All right, let's do a couple more here. 4x squared plus 20x plus 25. Okay, well, 4 is a perfect square, 25 is a perfect square, so I'm going to see if this is a perfect square trinomial. 4 is 2 times 2, 25 is 5 times 5. Since this is positive, it must be positive. Let's check it to see if it works out. 2x times 2x, there's my 4x squared. 2x times 5 is 10x. 5 times 2x is 10x. 5 times 5 is 25. 10x plus 10x, there's my 20x. That's exactly what we wanted. So this was, in fact, a perfect square trinomial, which means our answer is 2x plus 5 times 2x plus 5, which we can really write as 2x plus 5 to the second power. Okay, let's pick one more of these. Let's do letter F as our last one. 9x squared minus 60x plus 100. 9 and 100 are perfect squares. If they're perfect squares, there's a chance they are a perfect square trinomial. So let's try that out before we try any of our other options, right? Because there are other possibilities we could try, but since we noticed that these are perfect squares, we're going to start. I'm going to write some of the other possibilities just, to show you what I mean when I say maybe this will work, maybe it won't. Just depends on, just depends, okay? So, square root of 9 is 3. Square root of 100 is 10. And it wants to add to be a negative 60. If I want it to end up being negative, I need these to be negative. I'm going to multiply it just to make sure this works out. 3 times 3 is 3x squared. No, it is not. It is 9x squared. Double check, you guys. Don't go too fast like me. 3x times negative 10x is negative 30x. Negative 30 times 3x. Negative 10 times 3x is negative 30x. Slow down here just a second here. Negative 10 times negative 10 is positive 100. Now we're cooking. Negative 30x minus 30x. There's my minus 60x. So this is, in fact, a perfect square trinomial because it matched, right? it all worked out. So we know that 3x minus 10 times 3x minus 10, that's our answer, and we can write that as 3x minus 10 squared. So again, these are our special cases. Notice we still use that same guess and check, right? We think about what's going to multiply to be our a value, our ax squared, what's going to multiply to be our constant, which one of those options would add to be our bx. It's just if we notice, right? If we notice our perfect squares, maybe we can use that pattern and narrow down which option, right? Which option is our set of factors. Same thing here with that difference of squares. Maybe we notice that b term is missing and we remember, well, the only way for b to be 0 is if you had something minus itself. So we must be looking at those perfect squares and subtracting them, right? Or having one where we're adding, one where we're subtracting, so our b values end up subtracting. So it's just a way of, when we're talking about those special cases, it's just a way of narrowing down the possibilities. If you notice it, great. If you don't notice it, guess and check is going to get you to the same answer eventually. Okay, but like we said, the more familiar you are, the more we practice, the easier things get. If we recognize the special cases, it just makes those types of problems just that little bit more efficient, right? Just that little bit quicker.